this stuff anyways. Okay, so what are we talking about today is a great question. And we're going to be kind of talking about the same stuff as last class, but more formal. And so, still nothing to do with data. Well, let me give you the title. So the title, also, I haven't given a talk on a whiteboard in a very long time, so this should be interesting. Okay, so the title is going to be something like the representational.
Do you have any other monitor?
Is it bad?
It's not that visible.
Don't worry, I got more. So there's this word representational. Sometimes people call it expressive. So it's like a representational or expressive power of particularly the transformer. Okay.
Okay, cool. Maybe the black one was better.
Yeah? Or is it too small?
No, it's fine.
Okay, it's gonna be the title.
Okay.
Yeah. Okay, so maybe just like to keep in mind, so this stuff is gonna basically, okay, I mean, let me just write. So like, you know, we're gonna care about like functions. Just like, for now, they're just gonna map from, you know, some set A to B. And then we're gonna say, okay, like we don't have all the functions available to us, you know, like in machine learning we have function classes. And so we're gonna say we have like, you know, a function class. It's like a subset of all these functions, and we'll, you know, like in the transformer case, this is like sigma square, sigma star, sigma star. Transformer is gonna be like this subset thing. And like, the question, so there's all sorts of function classes, you know, you learn in machine learning, like, you know, the linear functions, like quadratic functions, neural networks. Today we're gonna have transformers in this function class. And we're simply gonna ask the question of just like what, wow, that's a good T. What F, or like what functions are in F? So that's going to be the question of today. And I just want everyone to keep in mind that like, has nothing to do with learning. You know, there's no data. There's no process of using that data to learn something. There's no computation. Like, as in like, you're not trying to like, use the data to run gradient descent to learn something. It's just going to be asking the question of like, does there exist, so let's say for neural networks, like a set of weights that can even represent the thing you want to do? That's why it's called like representational. So that's like maybe the first question you would ask. Like, you know, if you have a function class that are lines and then you need to represent like a quadratic, well then you're not in luck.
Is this kind of related to last class?
Yes, so last class is, I was saying like last class we asked the same things, like what kind of functions can we compute? That gave you like a rough idea to think of like transformers as like these, I guess, straight line program type things like RAS programs. And that gave you some like high level idea, and here we're gonna be very precise. And obviously there's going to be questions like, what functions should we pick to ask this question about? Or maybe like, should we compare function classes? Like maybe I want to see if like the linear functions are a subset of my functions. There's things like this. And we're going to make some natural choices, you know, related to actually the topic of reasoning and problem solving and so on. And we'll see that. Okay, so I'm going to start with a warm-up. Just like a super simple thing with neural networks, just to give you a feel of what's going on. So like there's a function that people seem to care about, and you're gonna see that it's sort of important. It's called parity, or sometimes called XOR. And parity is a function, right? And it's a function from bits, so like 0, 1. And let's just fix the input size for now. So like n length binary strings. And it outputs a number between 0 and 1. Okay, and the way it works is this follows, which is like the parity function with input, let's say, x, right? This is our n-length string. What it's going to do is it's going to output 1 if x contains an odd number of ones and 1 or 0 otherwise. Okay, so this is like also the XOR extended to multiple inputs. And so it seems like a pretty simple function. And so we might ask, like, okay, is this function like an element of some function class we might care about, such as like, let's say, single hidden layer neural networks, okay? So let's define the function class. I'm going to define a function class like calligraphic n, indexed by inputs of size n, and we'll leave a little argument for later. So this thing is going to be big, and I'm going to define things in like words, sort of. So of course these are going to be like, it's going to be the set of functions that map from like 0, 1, like binary strings of length n, to binary strings, right? And these are going to have like, it's not going to be all of them. It's going to be the ones that satisfy some set of properties. So it's going to be like the following properties. That we're going to say that there exists some parameters, I'm just going to call them theta, right? Such that my neural network parameterized by theta is equal to f. Okay? And then I tell you some properties of this neural network. So it's not going to be like any arbitrary neural network. It's going to be like where this neural network, okay, I'm not like, this is a neural network. You guys, I imagine you know what it is. We're not going to spend the time to define this, just the warm-up part. Such that the neural network has the following things. It has one hidden layer, and obviously a single output layer, because it's outputting a number between 0 and 1. And that hidden layer is going to be of size. This is the number of neurons in that hidden layer. And that's going to be like a variable that we're going to use S of n. It's a function of that input size, and we'll pass that in here. So now this is like a parameter that will make the function class like bigger or smaller. And of size like big O of this. So you can have up to that size, hidden layers. And one more thing maybe to this, like this is kind of like describing the whole architecture, right? Which is with what are called like sign or threshold activations. Okay, so that's our function class for this warm-up. And the sign activation is just like if it's a positive number, it outputs 1. If it's a negative number, it outputs 0. Yeah, so you have this neural network. And you might ask, like, okay, you know, for different sizes of the hidden layer, like, is parity in there? And there's some, I guess, classic results, which is like the following, like, if S of n is less than, like strictly less than 2 to the n, so an exponential, right, in n, well then the statement is going to be something like parity, which is just a function, right, is not an element of the neural network class with input size S of n, or hidden layer size S of n. Okay. And it turns out that the other statement, which is like, if it is 2 to the n, well then parity will be in there. And actually, if you have 2 to the n hidden units, you can express any possible Boolean function of length n. Yeah.
Can you remind me what's S? What does it do?
Oh, so this is just going to be like a function. So for instance, like an example, I don't know, like an example is maybe
This is just the size of the hidden layer.
yeah, maybe
How
I
many
choose
neurons you have?
n squared. So if my input is size n,
Okay.
then I say, oh, I'm allowed to have n squared hidden neurons, right? So my input's like 10, I'm allowed to have 100 hidden things, and that's not going to be enough. You're going to need exponential in n hidden neurons to model parity. So for that function to be in this thing. So this is already like, I don't know, this is kind of the flavor of things that we're going to see. Of course, the things that's going to change is that neural network is going to change the transformer, and these things of like one hidden layer, this size activations, there was a lot of like, Chava talked about bells and whistles, and we're going to have to pick which ones we care about. You know, like, do we use a layer norm? Do we have these residual connections, which maybe we talked about? What precision did we pick? Here we actually allowed the precision to be any real number, and that's actually fine for this. Like, we'll see, there's all sorts of these things, and we're going to pick some of them, And some of them we're gonna allow to vary, kind of like this. And then we're gonna see that as these things vary, like how does it increase the power to represent things and so on and so on. And as I can see, this is going to be tight on time. Okay,
That was
so,
the question.
yeah,
I was just wondering, because the input space is 2 to the n, right? So pairing,
No.
is it?
Oh, like the Boolean hyperstring.
yeah, there's 2
Yeah.
to the n possible inputs.
So then choosing the neural network with, like, the parity function somehow forces the neural network to make every node in the hidden layer, like,
That's
kind of
right.
make an
It's-
explicit selection.
So there's like, the number of inputs is 2 to the n, the number of outputs is 2. So the number of input-output behaviors is like 2 to the 2 to the n. But it turns out that like if you only have 2 outputs, all you really need to do is like just output correctly if it's just always 1 or something. So it's exactly what happens actually. The way it works is like you can, each hidden layer models like one possible output of parity and then it ands it all together at the end. And that's it. And you can model like Boolean expressions like ands and ors using the sign function, it turns out. And that's the argument of why you can model any Boolean function actually. Okay, and then there's lots of theory about this neural network stuff. I just want to, like, the thing I want to make clear here is that people have studied this. This is from like the 70s or 60s or whatever, I don't know. And there's all sorts of other things about like what happens if you change the depth. And then what if we change the neural network to like an RNN or an LSTM or convolutional whatever. And people ask all these questions, so this is nothing new. And all that's changed here now is like, you know, transformers came out. They're popular. People will obviously ask the question of like, what can we represent and what are they better at representing or not? And like, how does, you know, changing the depth affect things? How does changing the width? How does changing like precision change things? And how does adding like this autoregressive behavior change things? And we'll hopefully see the answers to all these questions today under a particular like architecture. Okay, so let's start with the transformer business here. And there's a lot of notation.
That's a homework, right?
Yeah, you can. That's just to get you, you know, to tease you into like the type of results that are to come.
It's good to think about this.
Yeah. Okay, so next thing, what am I going to do next? I'm going to try to define the function class for transformers. But I'm going to have to remind you what's in like neural network theta. I'm going to have like a transformer theta. It's going to be a bunch of parameters. I'm going to pick like the specific functions that we had before. Is like I'm going to define them like actually. So before we had like this key, this query, this encoding. I'm going to pick specific functions for it. They're going to be like matrices, basically linear functions. They're going to be parameterized by things. And then we're going to talk about, does there exist like a set of parameters that defines all these functions such that we can describe things. Okay, so that's going to be the story. So we need to define what is like, this is my goal, to define this like, and I'm going to use only a different notation for this name just so it's easier to follow. This is like the transformer, and we're going to parameterize it by theta. And this thing, if you remember, is going to be a map from sigma star to sigma star. And we'll change that later, because we're going to care about certain types of problems, but for now, that's what the transformer was, right? And this transformer had like, the definition of it was, well, I'll define it in this like compositional way. And that was that there was an, I'll do it from backwards to forwards. There was an unembedding that got backwards composed with the corresponding function at layer L composed backwards with the function at layer 1 composed with the encoding. Yeah. So input goes in here, it goes through all this stuff, goes out. I don't know, maybe just like it is important to just remember this because like it really looks like this, right? It's like this will drive our whole definitions in a second here. Okay, maybe I put this up at the top as like a small little picture to remind you of, and remind myself what I need to define. So you have these like encoding. It takes in as input some string W. So this would be like W1 up to Wn. Then it goes into like a layer. And this layer is going to be like f of 1. And then that continues. And you have another layer, or the final layer, which is f of L. And then we're going to have like these little unembedding blocks. And then maybe if we want to like just output a single token and do this autoregressive thing, we might just take like this guy at the end here. But keep this in mind, so we need to define all those functions, right? Which is like this E, F, and U. And so let's do that. So the encoding function, okay, I'm not going to define this whole like sometimes I'm not gonna define the whole input-output behavior of everything for the sake of time, we've seen it like a lot. Okay, so this input-output, or this encoding function is gonna be like a function of W. It's actually gonna be the addition of a token embedding function, which is gonna be parameterized by a parameter, so I'll put like theta token embedding. And that's just gonna be a matrix, okay? And that matrix will multiply W, and we treat W here, we're gonna treat them as like one-hot vectors that indicate the index of the corresponding like token you have. Maybe I just put it to be clear. Like,
So basically this is the W column of this matrix.
this W.
This multiplication. This data is the
So
matrix.
this is like a matrix, okay, maybe so it would be like this way, right? And this thing's gonna be like a matrix from R, it's gonna map you to R, okay. Let me define another thing, we have this workspace thing, right? We're gonna pick a specific workspace. It's gonna be R to the D, and R is gonna be changed momentarily, but for now it's like a D-dimensional vector space. And this is gonna be a matrix that maps you to RD, and it will take as input the cardinality of sigma. And this is to be interpreted as you've taken all the tokens and you've encoded them as one-hot vectors, as is done in like, I don't know, softmax regression stuff, or multi-class regression. Okay, so that's this embedding thing. There's gonna be like this token embedding, and there's gonna be some like arbitrary, like, I'll do it like this, like arbitrary function that's called the position embedding function that takes in as input W. And this will just be left as any arbitrary function. You have like all the power to make that whatever you want. Okay, maybe I erase this.
Wait, you call it position embedding, but it doesn't depend on a position, so that's, how is that going to work?
It
You
will
probably need
depend
to
on the
choose.
position. I guess we technically should pass in the.
Right. Yeah, you have to encode a position just in the input, but
Yeah.
whatever, right? Like maybe W also has a position.
Yeah.
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 And
that's
then the first one, the first theta takes this, and the second theta just takes the position, and like,
true. Yeah, yeah, yeah.
everyone's happy.
Yeah.
Okay. But,
That's
yeah,
a good point.
it's like, yeah. It's almost
Okay.
like, you know, like in RAS, you have the indices as
Yeah, yeah.
inputs 1 to n, and then,
Yeah, I'm trying to think of how people actually write this. Well, to be honest, I'm not gonna remember in the moment, so let's just continue. But this is gonna need to take in like the input size. Maybe I do this. Oh, yeah, you're gonna need to know the positions of the thing.
we'll figure it out later.
Okay, we'll figure out later. Just for, anyway, this thing is just like left as some any arbitrary function for like the remainder of this thing. So let's not worry about it too much. Okay, so then there's this this guy here, which is f of L. It takes in right vectors from RD to vectors to RD. It was like that layer thing, and it's composed. Well, it's made. It's defined, I guess, as the composition of like an attention layer, which what did we use for that? Is that A? Yeah. Attention layer and multi-layer perceptron. Okay.
Compose.
Composed together.
And it's not RD to RD, but RDN to RDN, but
Yeah. This is
just
great.
yeah.
So these were RDs, their workspace, and it maps n length or vectors to n length vectors, right? Yeah, and so these are like the things in visual. This is L. Okay, so then we have to define the internals.
That,
Yeah.
Isn't it strange that like in that thing the arbitrary function depends on W? Like why would you pick a linear function plus some arbitrary function, and why is the linear function even there?
This guy,
The second one, like shouldn't,
this one.
yeah.
Well, it should depend on the position.
Yeah, it should depend on the position, but it shouldn't depend on the actual symbol, right? Like the first one depends on the symbol, the second one should depend on the position.
Yes, that's right.
But if like, because if you say I have a linear function plus an arbitrary function, then I can just set the linear function to 0 and make it any arbitrary function I want.
Yeah, but it has different inputs, I guess.
But you're saying like they have the same inputs, W and
It
W.
should,
Yeah, it shouldn't. It should be like the indices, and I forget how that
Okay,
works.
yeah, that's fine. Yeah, as long as it doesn't depend on W on that.
Yeah.
W and I or something, or whatever, right?
Whatever.
Like the i's computation is.
It's gonna turn out not to be a big deal. Okay. So we need to define this like multi-layer perceptron business, and yeah, this thing is like, you know, it's defined for, okay, it's a single map. Let's define it. So this thing, just a single one, not the n. So right, this n thing was like, you do the like element-wise application of this. This thing actually works in parallel. So we used circle brackets. Okay, so multi-layer perceptron, just like a single one of them that takes in a specific RD, just like the embedding thing, right? There's nothing in parallel happening here. That thing is gonna go from RD to RD. And its definition is gonna be very specific. And it's gonna be the same definition that's kind of used in a lot of networks. And that's gonna be that we're actually gonna have the, okay, I'll put like xi as in like, it's the ith input. It's gonna have a residual connection, actually. And then to that, then we're gonna have like this single hidden layer ReLU network. Okay, and so there's gonna be a parameter W2, which takes the output of a ReLU, and that ReLU has a W2 xi plus a bias, W1, plus another bias. Okay, so this is just like, yeah, this is for a single index I, and yeah, and then you have them all, like n of them, in parallel happen.
Maybe it is better not to use the index sign in this definition, but whatever.
No, I just don't want people to get confused with the fact that we'll treat x as like an n-length set of vectors, and xi's are gonna be like RD things.
Choose, call it Z if you want to distinguish the n lengths, and because the I index would indicate that like somehow the index matters.
Fine,
Like,
people.
doesn't.
And so, okay, I'm seeing that, I'm not, like, there's parameters here, right? So like, this thing's gonna be, like, okay, I'm just gonna write it in the same way. So there's gonna be like this positional encoding thing that takes in the function. So the parameters here are gonna be like theta, t, okay, we'll group them up at the end actually. So, you got this guy, and okay, maybe I write the parameters. There's theta, and this is gonna be like theta of MLP, and there's gonna be one for each L, right, for each layer. And that's gonna be built up of like W2, W1, V1, V2, and so on. So I guess there's just these four. And then there's the attention layer. And the attention layer, okay, this thing actually operates on n-length sequences. And it has this definition, which it actually takes in x, and x here is to be treated as a n-length vector, or a sequence of length n with each element being a vector of RD. And we're gonna look at the I index of this attention thing. And that's gonna have, again, this kind of residual connection, xi. And then there's gonna be this whole sum from j equal to 1. And in general, you could have like, okay, well, there's different things. We talked about this. There's n. This is called cross attention. For the things we look at, we're just going to look at causal attention stuff. And so there you're going to have I, which is going to be called non-strict causal attention. And then sometimes we're going to have like I minus 1, which is for strict causal attention. And this will make a very big difference in a lot of results actually in the theory world, it turns out. That if you can or can't attend to yourself. Okay, so these are the differences. And in here you have like this function A of L, and that takes in a key and a query function, right? And we're gonna define these key and query things as just linear functions again, which are just gonna be matrices times the corresponding vectors. So here you're gonna have a key matrix or I guess the first one we had was query matrix. And that's gonna multiply the xi, so this is like xi gets mapped to another vector, probably an RD, and that's gonna ask for like certain keys, and the keys, there's gonna be a key matrix, and this is for a particular layer, and here you're gonna have the xj, so you're looping over all of these xj's, right, which is all the other like vectors, and you're comparing them to this, and then at the end, after you get this, whatever, somehow measurement of how interested the keys are to, or the queries are to the keys, you're then gonna have a value, and the value is also like a value function. Well, not like in RL, but you know, there's a function that maps things to values, and there's gonna be a matrix again, which is gonna be WV times XJ. Okay, and the okay, so that's the definition, and here's an important set of distinctions as well. So this thing is like, okay, what are some choices? We said that like, maybe it just gives you a binary value of 0 and 1. But in practice, like people will pick a softmax for this, right? And so if it's a softmax, then it should really like take in as input all of these instead. Like it should know all of the things. And so we're just gonna kind of, like, we're not gonna formalize that because it just gets ugly. But at the end of the day, right, this thing, it should, like, it can be a softmax. And if it's a softmax, well then it's gonna need to know what all of these things are so it can normalize by that. But all you need to know is like, the point is that this is going to be like, it's gonna, for every one of the keys, it's gonna be like a distribution of size I, and it's gonna sum up to 1, right? And so in some way, it's just gonna weight all the values by the corresponding kind of relevance, if it's a softmax. Okay, that's how it's usually done in practice. But in theory world, sometimes people simplify this in a way and say, you know, like the attention should really more or less like focus on one index, or maybe it like tries to evenly focus across them. So people will change this to like just a max, okay? However, if you have a max and there's a bunch of ties, then you have to resolve the ties. And there turns out to be like it matters a lot how you resolve ties in the simplification. So you could like pick the leftmost index thing or the rightmost, or you could take their average. And it turns out average is like a lot, like it's usually more powerful. And so people call this like average. And instead of softmax, they call it average hard attention.
Sorry, average over what when they are equal?
You average over all the values that are equal, and you take like, you basically split it up into a uniform distribution. So if they have like 3 things that are, if there's 3 maxes, then you split this calculation into like 1/3.
Oh.
Right, so once again, if when you do this thing, it turns out that, you know, these are gonna be, okay, these are actually gonna be like dot products with these things, right? And you get a number, and there's gonna be a bunch of numbers for every single one of these, and then if this number turns out to be a tie for the max, then this A of L will allocate its distribution that has to sum to 1 evenly across all of them. And that in some way, if you like want to attend evenly to everything, you can actually do that here, right? You can literally split it up perfectly across all of them. Yeah.
Is the dimensionality of the workspace usually less than the number of tokens that you have?
I don't know. Like I know in GPT 3.5, like this thing was like something like 13,000 or something like that. And I think the input length was like 12,000, but I don't know what it is now. Like, yeah. But if any of you like look at like, I don't know, like the Llama herd papers or like DeepSeek, you can find out. It's probably more than 13,000 now. And then like, but the input sizes are now in the millions, so it seems like it's gonna be, I don't think it's a million though. D.
I meant the size of your alphabet. Like, do you get a reduction from moving from the token space into the workspace? Do you get a reduction or an expansion?
Oh, so you didn't mean N, I don't know if you said N, but you meant like the cardinality of sigma.
Yes.
I think like the tokenizers they use these days is like 50,000 tokens or something.
Okay.
But now you can encode things as vectors, and so there you can, I don't know. Things are better. I don't have much to say. Yeah.
to clarify, so when you're talking about this max and softmax and average, that's all max of the attention number, right? Like that's the AL number?
Yeah,
Yeah, so like this, you know, is gonna calculate like the softmax calculation for a particular key. You really should do it for all the keys in the sum, and then like apply the softmax, right? And yeah, so this would be the average over all the keys times the single query.
Right, so the weighting of the value in the final result depends only on all of the ALs. It doesn't depend on the keys or the values or the symbols or anything.
That's right. So this thing will do the weighting, and that's gonna weight these values here. Okay, so I think that more or less defines the transformer. There's gonna be one last thing, the unembedding. And the unembedding for, I mean, it's gonna take this, okay, well, it takes this, right? These things are done like element-wise as well. And for us, it's gonna map it to a number that's the size of this token space, or alphabet, or vocabulary, or whatever. And that's to be interpreted as like this one hot vector way, and then you can do the unmapping afterwards. And the unembedding will be, like if you plug in Z, it's gonna be just, it's gonna be parameterized by another parameter called theta unembedding, I guess. And theta unembedding is gonna multiply the Z. And then you're gonna take the max over
argmax.
Well, we'll do,
I think it's an argmax over the
I think,
components.
we'll do it like this. Which is, okay, so you have this data, there's that embedding thing, you multiply by Z, this thing, this matrix, I guess, it is a matrix, is gonna be from R, right? It's gonna map you to the size of the alphabet, and it's gonna take as inputs D. And now that you have this thing of the size of the alphabet, you wanna look through all of its indices and look at the largest kind of like valued thing, and yeah, and then you take the max. And so you get the max index, which is what we wanted, because this is numbers.
But you wrote the max by.
Yeah, good point. Okay, so argmax index. Okay, great. Okay, so that's all the parts. And okay, we talked about some things that matter, and these are important. So this thing, maybe I should write in green. So these will matter. This will matter. These we're going to change sometimes, and there's going to be all sorts of other things. So let me write down all sorts of other like architectural parts that are important.
You can write again with black and see.
Sorry?
Maybe you can write again with black and see how it works.
Okay.
Why? I also already have black. So you can try mine.
Yeah.
You add the layer to some of the weight matrices, but not some other. Was that intention?
No.
Okay.
These should be. Okay, and then the
Maybe this is better.
Yeah, that's pretty good.
okay, and the thing to point out is at the end you end up with a ton of parameters. This is what I want. This theta, what is this theta thing that the transformer is parameterized by? Well, the theta is going to be like, you know, this giant sequence of like the token embedding theta and the theta positional embedding and the theta MLP, layer L, and the theta for the attention, which, okay, for layer L, which is just going to be like gather up all these matrices, theta, attention, layer L is equal to like W key, W query, W V, and then like theta on embedding, and that whole thing, yeah. Okay, and this is like your sequence L element of number of layers. So you gather all those up, and you have your parameter. Okay, so you know, if you set a different parameter, you get a totally different transformer. And roughly speaking, the function class is going to be like the set of all transformers for, you're going to fix some architecture, and you're going to say like, does there exist a parameter setting to then describe some function? Yeah.
I remember correctly, in the previous lectures, you said that there is some like weight sharing in the architecture.
Yeah, so the weight sharing is the fact that,
Different weights for every layer.
no, there's there's different weights for every layer, right? However, no matter the input size, right, the same weights are used. So it's not like you have different weights for different input size. Like you fix a matrix, and then you do this calculation for like the multi-layer perceptron for like, right, this, like in here, there's like a little multi-layer perceptron guy. Well, I guess it's after the attention part. And these are all the same. Like these are all MLP blocks here. And they all have the exact same weights. And so no matter the length, the MLP is always going to use the same weights. And similarly, no matter the length, these W's are always the same. The difference is, like, I mean, they obviously differ by layer, but they don't differ by sequence length. And that's the thing, you can process arbitrarily long sequences. Okay, and so there's a bunch of architecture related things that we can talk about, and I'm just gonna like define them. So like, I guess these are like,
This black might work better.
there's all these architecture things. Wow.
Yeah.
And I'm just gonna put a bunch, like some of them that are important. So there's like the depth of the transformer, right? The depth L. And we're gonna treat that as like a constant that you just like fix beforehand. Similar to like the neural network, we fixed that exactly there's one hidden layer. And we're gonna vary it maybe near the end. Then you can vary what we're gonna call it like the width, or sometimes the embedding size. And that's the dimension D. And we get into the first kind of like argument of the thing that, okay, there's gonna be these architecture things, like ideally, there's no dependence on n, right? So if you change the input length, ideally your architecture doesn't need to change, right? Like the idea is like you're gonna have an architecture that's just fixed, and then for any sequence you can do this processing. And then we can all like, okay, that's like the idea, but then it turns out, is that reasonable to kind of ask for? And the first answer that people like in theory will say is like, well, if your width D doesn't depend on n, well, you run into issues because this positional embedding function, right, needs to map to like a different number, or like it should be able to like ideally it should be able to map to something different for every single input. And to be able to do that, you're going to need this to depend logarithmically on n. So you can use a different binary number for every single position. Okay, so this turns out to be like kind of the minimal assumption that people will make on the width, because otherwise you can't encode the positions. Right, if you have like a length n thing, you need log n bits to encode just the position that each token is at. Okay, then the next thing people talk about is precision. And so yeah, this is gonna be like the minimum, we might even make it bigger. And then there's precision, which is like the precision of the actual weights or the numbers you're working on with like on a computer and stuff. And so you're of course not operating with like real numbers in your workspace. And instead you're gonna work with like some like floats or ints or something like this. And so we're gonna have to choose like a precision. And roughly speaking so we're gonna change this R. This R here is now gonna change to like some sort of whatever data structure, choose an int or something like that. And we'll just describe it's gonna be like 0, 1. Now, and then you have to choose some dimension. And okay, so then you wanna maybe make a constant, something like, I don't know, 8-bit ints or something like this. And we're gonna see what happens when you do that, and that should be kind of okay. But then there's an argument which is, we might want this to be like at least also logarithmic in n for the following reason, which is that this thing is gonna be like the attention score or whatever is gonna be represented by a number, right? And if there is n possible things you're attending to, right, at the final thing, and if you wanna like, let's say, do something called average attention, which is split the weights evenly across everything, well then this number better have precision at least log n. And so sometimes we'll talk about this as like constant or log n. And we'll see how this affects things. And otherwise, the things that we will always use is, so we're always going to use a layer norm. And there's very different versions of layer norm, like pre-norm and post-norm and so on. And I'm not going to tell you which one, but like layer norm gets used in all these things, and we use causal attention, as we've seen. And the other argument is like, as long as, so you might want to use multi-headed attention. And so we're not going to use multi-head attention, but the argument is that it's actually fine as long as you have a constant number of heads that doesn't depend on input size, then you can always simulate it with single head attention by just adding that many layers. And so like these things, since the layers will be, depth will be constant, and this is constant, it's fine. So in some sense, we kind of have it. Okay, so these are all the architecture things. And okay, so now we need to define our function class that contains the transformers. Okay, let's do that. So I'm going to have a function class tau. And the things that we're going to talk about varying for now is going to be like embedding size and precision. And so I'm going to have a function here for embedding size, which is d of n, just like I had for the neural network, for the number of hidden neurons. And this function class is also going to depend on the precision p of n. Okay. And now this thing is going to have like, you know, a similar style definition to that guy over there, which is, you know, it's all the functions from, okay. Let's do sigma star to sigma star for now, and we'll change this soon. So it's all these functions such that there exists a set of parameters theta, right? We know what theta is now here, such that the transformer function parameterized by theta is equal to this f here, so it's sort of and the other property is that where, okay, now we need to talk about these variables where t, the transformer, has big O of d of n precision, or embedding, or let's say width, big O of p of n precision, and that might be all. Yeah, that's it. So these are going to be the two things we vary, and then everything else in the architecture, I told you what it is, which is like, you know, this is going to be some constant. So you could, I technically should be writing O of n depth and O of 1 depth and so on and so on. So I should technically write like O of 1 depth and whatever. But the point is, these things like don't depend on the input size. Yeah.
This is really weird.
Why?
Because f is a function from strings to strings of any length.
Mm-hmm.
But n is part of the specification of d of n. It's like d is like how the width is going to grow with n,
sure.
and how the precision is going to grow
Yeah,
with
yeah.
n, and like
Okay, fine.
so is this like no uniform class? So if like the part of f that's on sigma n is something like
Yeah, something like this. So you restrict your transformer to inputs
right.
sigma n, and you want them to be equal for all n, element of, let's say, natural numbers. And then like, such that on input size this, it has this width and so on.
So this weight is, so it's a single, it's not a single set of weights for every n. You should have some weight, like without loss of trinity. So it's the other way around, like for every sequence size n, there exists some weight.
Yes. No. We're
Because, for example, if the width changes, then the dimension of my matrices change. So does this mean that I should have one infinitely large matrix? Or do you see what I mean? It's like,
yeah.
what's going on?
Yeah, maybe the for all n should come first.
Yeah, I would think that.
This is more
let's try
restricted.
that.
But then it feels like it's
Then we are cheating too much.
that they're non-uniform.
Yeah. So yeah, like what's uniform if you allow the width and the precision and everything change, then there is nothing much uniformity on.
Yeah. Well, it's uniform up to that length. So you like have a transformer that like up to whatever length n can solve all the problems, but then if it gets bigger, you have to pick a bigger one.
this definition doesn't express that, but
Why don't you fix the input to be, instead of sigma star, to be sigma to the n?
the basic problem is that we want to talk about transformers that do not change what they compute, how they compute, as a function of the length of the
Yeah.
input. But now we are facing the dilemma that you want to increase the widths with how many inputs you have, or like how long the sequence, and that just conflicts with this view that like you should have a uniform way of processing sequences of all lengths. So that's kind of the fundamental dilemma. It's kind of a subtle point.
Yeah. Well,
So once you break the uniformity, you can break it in any ways. It's like then it's just kind of gone. But still, like, yeah, you want more uniformity than less uniformity. Like, you don't want to say that like, oh, these transformers for every size are unrelated to each other. And now the definition kind of allows that.
yeah, so for every input size, you can have a different set of parameters.
But I think that like it's kind of like what you said,
Yeah.
what that like
Yeah,
up
it's
to a
supposed to-
size n, you have to use like so
It's
it's
like-
a union of all m smaller than or equal to n. So that strengthens the definition, right? Like then for every sequence of up to length n,
Mm-hmm.
you have to have a transformer that does the processing in the right way,
Yeah.
not just for that sequence length. Then it's kind of more uniform in a way. It's somewhere in between the absolutely uniform way of processing things and
Yeah, I don't know. I guess I should write like for all n, there exists a theta subscripted by n such that.
just change the restriction to sigma n to restriction to union of sigma m where m is up to n. Like sequence is up to length
And then this is gonna be from like
m, it's m, right? Like a new index or something
m equal 1
to
to
n.
n.
Yeah.
Yeah.
I think this is the best. I think this is what people do.
I think so. They put it in words. Like they give you a nice paragraph all the time.
Yeah.
And then you try to parse the
And then you have to
exact-
read the proof to understand what they do.
Yeah. Okay, so
Graph size.
Is the intention here that if you increase n, then the new class of functions includes the old class? Like, so if you have like a bigger function, should it give the same result on a short string as like a shorter function, like a smaller function? Or something, is that uniformity condition?
But you can't have that.
I
Like
might-
the domains say.
Yeah, but the bigger class can also always process smaller strings, right?
Yeah.
But here we are not saying that there needs to be any connection between these two classes.
It's somehow, it's like this definition is kind of working the other way than what you're proposing. That might also work. Because there you could just say, let's take a look at all the functions that you can represent with a fixed number, a fixed width, and a fixed precision, D and N. Just call it like that.
Mhm. Yeah.
Okay. And somehow you take some intersection of these as like D grows and P goes. Like you're interested in all those functions that have consistent continuation in bigger classes.
Yeah, well, okay, maybe let's, I will say there's, like, the first thing I wanna talk about, they allow a different transformer for every n. So it's not even gonna be this definition. And then the second one is gonna be this, but, okay, maybe, yeah. Okay, so there's this thing, I really wanted to write, all the function classes that we're gonna talk about on the left here, and, we have 30 minutes to do that. I'm gonna erase all this, actually, and now move on to, like, the question of like, what functions should we ask if they belong to this function class? Really, because like there we chose parity, and that was maybe arbitrary. And the question is, should we pick other functions? And another question is like, maybe we should compare this to function classes that we're familiar with for some in terms of like doing something. Okay, maybe I should have been erasing while talking, but. And so the thing we're gonna do is we're gonna care about, let's say, the reasoning style problems, because that's the point of the class. And like, what are reasoning problems? Well, I don't know, like, I can give you some examples of problems that you might think require some reasoning. So maybe like multiplication requires some reasoning. You know, you have to think about all these like procedural steps. Maybe computing parity also requires like some reasoning. Another problem is like, let's say you have a graph and you're given like 2 points in the graph and you need to figure out if there's a path between those 2 points. So maybe you're seeing that I'm going to this like idea that, you know, the reasoning problems are going to be those that are kind of like what we know from algorithms courses and so on. So this is where the whole models of computation stuff comes in that you might have seen about today's topic. And so the question is like, what functions should we care about and so on? And maybe it's going to be like, we're going to care about functions that represent reasoning problems. Something like this. And yeah, so some examples, let me just give you like two very quick examples. So we've seen parity, right? It's just like, I guess we've seen it, so I don't have to write it. There you can represent the reasoning, like the problem. You can think of a function as representing a problem in the sense that this problem has a bunch of, like any length n string it can take as input, and it should produce a corresponding like correct behavior. Okay, so there's going to be this mapping between like a problem and a function. So another example of like a problem is, for instance, like graph, let's say it's called graph reachability. And the way this works is like, it will take as input like the graph as like maybe this like adjacency matrix thing and its vertices, and then describing the edges, and then it also needs to take in a point S and T, and the output should be, and I'm just like very high level explaining just the fact that you can think of problems as like functions, and the output is going to be 1 if there exists a path from S to T, and 0 otherwise. 0 else. Okay. And you can do this for like a bunch of your algorithms problems. You can think of like all your problems as having some, okay, so then what's the input space here? You should think of it as like sigma star, and you've encoded like all the symbols in your adjacency matrix and the points as something in your alphabet, and it outputs like 0, 1. Okay, and it turns out that like what we're going to talk about is really problems from like complexity theory type world, which is, okay, so this is like one example of a very important problem. Another one's like maybe the 3-sat problem, and I'm just going to write it here. That's the thing, which is like you have this like Boolean expression of ands, or it's a bunch of ors of ands where there's 3 variables in each of them, and you just need to answer, is the expression, can you satisfy it? Can you make it equal to 1 or not? And what I want you to see is like this thing is also a map from sigma star to 0, 1. And actually all these like complexity theory thing more or less worry about decision problems. So it's either 1 or 0. And the other thing they'll do is they notice that if your alphabet is finite, which it is for us, we're not going to allow that to scale with n, well then you could always choose whatever like the length of your alphabet is as the corresponding like numbers you need to represent, then pick the logarithm of that as your bit length to represent things, and you can always talk about this as just being the binary strings from 0, 1 to the star. Because you can encode every single element of your alphabet with like a finite length binary string. And so, okay, so these are going to be our mappings, and for that reason, we're going to compare transformers to this. And so our transformer is now going to be a mapping from 0, 1 to the star, as there. And now this thing, instead of being like this parallel mapping thing, it's going to be just the last token. So just visually, if you had that diagram, it would just take the last output of the last embedding. Yeah. So that's going to change to 0. And now we're just going to ask, in this like complexity theory world, what do we know about these things? And I give you a quick rundown maybe of some things that we know. Okay. And then we're gonna try to relate it to the things we know in complexity theory. Because that's a very like rich field, and we know like what kind of problems are in certain function classes, like quite literally, they call them complexity classes. And we're gonna try to compare things to these complexity classes. Yeah.
So essentially, like this definition is saying like reasoning problems are decision-making problems, and that's
Well,
what-
I'm just like making this high-level meta claim that like maybe the reasoning problems you care about, some subset of the ones you think are interesting, or like decision problems. And you can think of decision problems as just functions, and that's beautiful because now we can ask which decision problems belong to our function class. And it turns out that people have already studied this like quite in depth, and they define their own function classes in complexity theory based on their own models of computation. And a model of computation, roughly speaking, is going to be like some procedure that takes some input and then produces a mapping to 0, 1. And so I give you two models of computation that you've probably heard of. One is a Turing machine. And you can define function classes depending on how much resources you give to a Turing machine. Okay, so you should roughly think of it as like, okay, it's just like a finite, this is what we're going to think of, it's like a finite state machine with infinite memory, or unbounded memory. Roughly speaking, like, here's an example of one. This is computing parity. So the way this works is you have to define your state machine. There's going to be two states. This is the state of like even, and this is going to be the state of odd. And then if you read your input, okay, and there's going to be these tapes, which are your memory. This is going to be the input tape. So you put your input, this is the input tape, you put your input on the input tape. The Turing machine reads it, and what it does is every single transition or step of the Turing machine will read something from a tape, move the corresponding head of the tape somewhere else, and do a transition in the finite part of the state machine. And so yeah, so the way this finite state machine is going to look is like, if you have a 1, you go to this state. If you get another 1, you go back to the even state. And if you get a 0, you just stay in the current state, which describes exactly the parity function. So with just two states, you can actually encode parity. You don't even need these tapes, but for harder problems, you will use these tapes. And the story is you have this like extra tape in the middle for your workspace, and then you have an output tape, which outputs the corresponding like thing like 1 at some place. And this is one way to think of Turing machines. Okay. And there's different, like, and similar to like the transformer, there's different resources here that we can talk about how like changing that resource will change our function class. Okay. And so the two resources for Turing machines is going to be the number of transitions it makes in the state machine and writes to the tape, and the amount of space it uses on the actual tape. Okay, or like how big of a tape do you really give it? And we're not going to talk about the space thing that much, but we'll talk about the time one really briefly. And so there's a function class that's defined as deterministic time. It's going to take as input t of n, like this function that tells you what is the scaling you allow for time. And I really wanted to define this here so that we can compare them. And deterministic time for a parameter t of n, and just remember this is like with, oh, well, I mean we know it in the definition. So there's this thing, and that's the function class that there's same way as above. But now the property is such that, right, there exists some Turing machine. There exists a Turing machine such that a Turing machine is equal to f, and the Turing machine transitions t of n, big O, t of n times. Okay. And the cool thing is this class, like immediately, gives us a well-known thing you probably heard of, which is the class P. People ask whether P equals NP and things like this. And P is just the union of all these deterministic, okay, greater than equal to 1 of deterministic time. And then here, it's all of the possible polynomial functions, n to the I. So we allow like linear, squared, cubed, and so on. So this is P. Okay, and so we're gonna compare this to the transformer at some point. Good. That's all I want to say about Turing machines. I want to define one more model of computation. Do I want to do that? Well, you know what? How about I tell you, okay, let's get through at least something. So let's do that. So there's another model of computation called circuits. I'm gonna skip them for now. And I'm just gonna tell you about how these things relate to Turing machine stuff, because they'll very beautifully lead into like what Dale is gonna talk about next class, and you can actually see what's the difference of what he's talking about and what I'm talking about. And then we'll see how much time we have for other things. Okay, so there's these Turing machine stuff. Okay, so how is this gonna work? Well, it turns out that this class is like very weak in some sense. Okay, so I was gonna put the results on this board, so maybe I'll put them here. Okay, so the first thing is like this T guy. If I plug in log, or even worse, like if I plug in actually poly, and this is like poly n here is gonna mean like take the union of all polynomials, just like we saw there. So I allow polynomial in n scaling of the embedding or the width d. I'm gonna use log n precision. And I'm gonna allow t to be completely non-uniform. So for every input size, I can pick a different transformer. And this is called like non-uniform. This thing is like a strict. Okay, it's a subset of P. We don't really know if it's strict but it's actually even like significantly weaker, and it's based like, let me just write this thing about circuits. There's like these circuit classes. I'm gonna just write a circuit class for now. There's a circuit class called like TC0, which is quite weak. It's like circuits that have constant depth, and that's believed to be much smaller class than P, and so this isn't. So that's what I want to say about that. And then the thing, okay, like, yeah, in terms of time, I really want to define the circuits, but I don't know if it's going to be possible.
So that precision was the power of 0 and 1, right, for the workspace?
Precision is the power of, yes, like the integer size that you're allowed for the workspace, and then you raise that to the d. So instead of r to the d, you have like integers of length n to the d. Log n, I guess. For that. Okay, so turns out this is like a very weak thing. The circuit, like roughly speaking, the circuit is like, it's any circuit that you can draw that has finite depth, and it looks like this. So this is what the circuit would look like. You just like, okay, you have your inputs x, so maybe you have like x1, x2. Then those will go into like some AND or NOT gates. So like here you might pick this is a NOT gate. Maybe this goes into here, this goes into here. Then you can put like an OR gate, or maybe I think it's an AND gate. And here you put another like AND gate, for instance. You have this path, maybe this path, and then maybe you put like another OR gate here. This turns out to actually compute parity for input length 2. This circuit. And the important thing is there's measures of resources, like Turing machines for circuits, and there's one of them which is like the depth, and the other is the size. And the depth is like the length of the longest path, and the size is the number of gates. And so this TC0 class, the 0 means that it has constant depth, If you change 0 to like 1, then it has logarithmic depth. If you change it to 2, that means it has log to the power of 2 depth, and so on. Like log n, all power 2, and so on. And TC0 allows not just AND or and NOT gates, but it allows like one more gate called the majority gate. And yeah, and it's considered to be like quite a weak complexity class. And so these transformers are in this class, and maybe it shouldn't be so surprising. I guess here's the like highlight thing, is that it turns out you can really view these transformers kind of like circuits. Like this finite depth thing really represents the fact that transformer is kind of finite depth. Yeah, the size thing here, their circuits, TC0 is going to be the circuits that are allowed to be a polynomial size, and the size kind of is like the same as the embedding size here. And yeah, so there turns out to be a very rich relationship of like all the stuff between circuits and and transformers. And so, yeah, like another thing is graph reachability, this problem, which is also like pretty easy to solve actually, is very likely not in TC0. Okay, anyway, so this is all to highlight this class is quite weak. And so the next question you would like ask is like, what can you do to this transformer to make it like more powerful? Because right, at the end of the day, all that we're doing here is like we said, the transformer gets one pass of its, like this input, it gets one pass and outputs the correct answer immediately. And so you can imagine the obvious like answer is, we actually use them in this autoregressive way. And people call this usage of them like chain of thought. And so the natural question is going to be like, does chain of thought buy us anything? And it's going to buy us a lot, is the answer. Okay, and so I'm going to define this function class called chain of thought. And maybe the best way to define it is through a picture, because writing everything is going to take too much time. So chain of thought is also going to have some number of steps t of n. And it's just going to be applying the transformer autoregressively this many times. And then you also have the corresponding same things like the dimension, the embedding size, and the precision. So you have this extra parameter that's now going to like make use of the transformer in this like autoregressive way. And so I just draw like the picture. It's like if you have a transformer, let's see. You have a transformer. This is like your transformer. Parameters theta. So the thetas are going to be, you fix the transformer, right? So just the same way as this. You're going to take this transformer. This guy's going to be an element of t for the corresponding d of n and p of n. And now, this is going to define a new function through like applying this fixed block with the same parameters multiple times in the following way, which is like you're going to take in as input some w, let's say. Okay, so w comes in. You want to look at it like w1 up to wn. Then it's going to output just one thing, which will be called wn plus 1. And then that's going to be passed into the same transformer, still parameterized by the same theta. It can take any input length, and now the new input is going to be this w1 appended to w1 to wn. And then you do this repeatedly, and it goes up to, and then you do this some amount of times, and the amount of times you're going to be allowed to do this so wn plus 1 is going to be, roughly speaking, n plus big O of this t of n function. So if like t of n is n, then you can allow another amount of, as the same size as input size of autoregressive steps. And then the final thing is going to be your output, which is going to be like, yeah, your output, whatever. Okay, so this is how this t of n is going to interact. It's going to tell you how many autoregressive steps you're allowed. And the question becomes like, what can we do with this chain of thought class, and how does it improve things? And the answer is going to be, it's going to improve a lot. And so it's going to look like this. So deterministic time Turing machine, like the class deterministic time. And here's going to be, so if I allow t of n, and I put this restriction that it's greater than n, so any function is greater than n, like n squared and q, whatever, So if I plug that in here, then that is a smaller class than chain of thought, T of n. And the question is like with what embedding size and what precision? Well, it turns out that it's actually not that constrained. You can actually have an embedding size of 1 and you make up for it with this logarithmic precision, and that'll actually be enough. And then the cool thing is like then this thing can be simulated by the class deterministic time with argument t of n plus n. That's its argument. Both squared. So something like if you said had linear runtime, like a linear runtime Turing machine or computer, then you can simulate it with linear number of chain of thought steps of your transformer. And this is getting like interesting now, like right, the mapping of deterministic time is like a computer that takes kind of this many steps. And now the mapping here is that my transformer that takes T of n autoregressive steps can simulate any computer, kind of any Turing machine. And it turns out a Turing machine can also simulate that with just like a quadratic overhead. And this is really this tilde means that you exclude log factors. Okay, so that's the thing. And this immediately implies
Exclude?
like you hide the log
Oh,
factors.
hide.
Yeah.
Okay.
And so this immediately gives to like two things. Well, like that what that tells us is that if I take the union of I greater than or equal to 0. Oh, and just notice that this class, if you plug in T of n equal to 1, well actually 0, so like it's exactly 1, then you get exactly this class that we had before, which is just exactly one autoregressive step. Okay, so if you take the union of I greater than or equal to 0 of chain of thought of n to the I, and then the same things as before for those, this exactly equals to the class P. And yeah, and you can do a similar thing if you wanted the class X exp, which is the exponential runtime things. And you can take this actually to kind of the extreme, which is that if, okay, so that's good. And then if, let's say T of n is unbounded, which maybe you plug in like chain of thought infinity or something, then chain of thought, let's say like of this infinity or whatever, is what is called Turing complete. Or it can simulate any Turing machine. Which in other words is if you define the function class, which is the set of all functions for which a Turing machine can represent, then a chain of thought can also represent all those functions. And just one note, like the Turing, just maybe, okay, we'll talk about that in a second, and how it relates to Dale.
I didn't get this statement. Is this T of n unbounded? Where is T of n in the statement? It doesn't appear as well.
Yeah, I should just put T of n.
If Tn is infinite or something, or
Yeah.
Okay, so if Tn is like the union over all Tn's of all the chain of some things, that's Turing complete. That's what you mean,
Yeah,
right? Like there is no restriction on the runtime.
yeah, there's no
There is no restriction on the growth of the runtime, but there is some runtime.
Yeah.
Then it's Turing complete.
Yeah,
Okay.
What's
Yeah.
this walking paper?
So for all non-negative functions, including any
Yeah.
growth, the union over all those Tn's chain of so T of n equals or
Yeah.
like it's a superset of the
it's like
everything that can be
T of n
computed in
and
Turing machines. Yeah.
This is T of n.
The Tn thing, it should literally be infinite, right? It's like Turing machines don't always stop. There's no way it's
No,
always
that-
union over finite time, that seems off.
Okay, so how is Turing complete?
Basically,
I think that you
Well, we
can
only look
simulate
at
any
the-
Turing machine for any number of
We're only
steps.
looking at the functions for which,
That's Turing complete.
like, I guess that
In
we,
this case.
Please have to.
Chain of thought doesn't have a origin there.
Yeah, but that means Tn would literally be infinite, not just unbounded union thing. Right?
yeah,
That means it's always halting if you're taking a union over really fast growing functions. Like, I think
Yeah.
infinity is better than the TN, that's all I'm complaining about.
Yeah, maybe it's like
Okay.
literally you have to, but like you can't put infinite there because it has to.
I'll just be
I mean, like the thing was not
Okay.
defined. I mean, like maybe it's defined. Like it can output an infinite string in autoregressive mode, and if you allow that,
Yeah.
then it can
Assuming
do the
you
same
have
as
to
the
allow
Turing
that.
machine.
It would be like a coup if you cleaned off all of it.
Well, like,
Yeah.
I mean, the way it works, okay, the way it works is literally this transformer just mimics the transition function of a Turing machine. Exactly.
Right.
And that's how you prove this. You just
So
say
that that's like literally T, no restriction on T of n.
Yeah. Okay, so that's the statement. I just wanted to mention, like, also that, in case you didn't know, Turing machines, like, the set of functions that they can represent is not all possible functions, right? So, like, there's a classic example of, like, something called the halting problem, which is a function that is not computable by a Turing machine. So it's that itself is not containing all the possible functions. And so, yeah, there's this statement. And, like, the way this should be interpreted, right, is that there exists a transformer with logarithmic precision, constant width, dimension d, and all the other architecture things, as we said, such that if you allow the chain of thought to be unbounded, right, then, like, yeah, so there's transformer, whatever, so, and then if you set all those things, there's going to exist some set of parameters, right, thetas, that will allow this to be, like, Turing complete, right? So the whole claim is that there going to exist some set of parameters
Yeah.
such that all, like, that stuff holds. And so the thing that I haven't told you at all is, like, whether we can actually find these parameters by learning from data, whether you can, like, then efficiently use the data to compute the parameters using gradient descent or something, and so on. And so all I've told you is that there exists some set of parameters to do this. And what Dale is going to tell you is that, well, like, what would be a strong claim? The strong claim would be like, well, you know, we've trained models already. And like Gemini, well, he's going to tell you exactly, like Gemini 1.5 is a model that's trained and has fixed parameters already that have been learned and whatever. And you might ask, is that model already Turing complete? And he's going to claim that it is, in this autoregressive way, more or less. There's going to be like some caveats on how the autoregressive behavior works. But he's going to tell you that, like, whatever this thing that I told you that there exists a set of weights, he's going to actually tell you that, well, the weights that are set in Gemini 1.5 something, whatever, they actually satisfy this, like, Turing completeness, and it can simulate all the steps of a Turing machine. Then maybe you'll talk about some other things about how actually if you randomly initialize any transformer, then it is also still Turing complete. Yeah, that's what I wanted to say. I wanted to say one more thing, really high level. So, yeah, there's a lot of stuff about circuits that I didn't mention, unfortunately. There's a lot of beautiful results saying that transformers are like transformers, okay, I'll just say in words like these, if you have log n precision, then they're exactly actually equivalent. Oh, I didn't write this, but they're actually exactly equivalent to TC0, so this is really beautiful. And if you change the precision from log n to constant, then they're exactly equivalent to circuits that don't have the majority gates, that are called like AC0 circuits. And so there's this beautiful literature with now chain of thought that people have already like talked about that I didn't get to talk much about. And then after that, people are like, okay, like at the end of the day, we do this autoregressive way. And you might still have the question, okay, like it's kind of unfortunate that you have to like, you know, oh, there's one more thing that I should tell you. Oh, I'm really running. Oh, well, I'll leave it as a cliffhanger. So this guy here, you might ask, okay, like I don't want to use like linear chain of thought. You know, that's a lot. Like my input size 1,000,000. I don't want to do 1,000,000 things to do XOR, or like a parity of 1,000,000 binary things. Maybe I want to use a logarithmic. So maybe, like, let's say okay, maybe I should hide this. What if I define the class chain of thought log n, right? And then like same exact things, like literally poly n, embedding size, log n, precision. Well, it turns out this buys you absolutely nothing, and it's exactly equal actually to this. Okay, so that's a thing. And then the next thing would be like, is there like, you know, you have this fixed transformer. We chose one way to reuse it multiple times, and that was chain of thought. And it seemed a little bit sloppy, maybe. You know, you like you only take the last output, you pass it in, reuse it. Can we like reuse the block in another way? And the obvious other way that you might have started with is the following way, which is like you take the transformer and you literally just pass in its outputs, all of them, into the transformer again. And you do this a bunch of times. And then you take the output at the end. So there's no autoregressive thing, it's just like, you basically artificially give it more depth, right? And this is called like a loop transformer. And this is another way to, in some sense, if you have a fixed transformer, make use of it like multiple times, the same block over and over and over again, so you don't have to retrain anything. And this turns out to be actually more productive than chain of thought. So like, it'll be a bigger class than TC0. And like, for instance, graph reachability, that problem is likely outside of TC0. And this type of transformer with only log n number of repeated blocks, which would be compared to this, can actually solve graph reachability and things like this. And yeah, so this is like a cool line. And just to mention maybe like how recent, so this stuff here, this is like, okay, like this exact stuff is like 2024 by this guy named Will Merrill and Ashish. And this stuff is like literally from a few months ago by Will Merrill as well. And there is, I want to mention like actual people in empirical world that implement transformers in this way, like loop transformers, and they actually have implementations on like 8 billion models, and like 8 billion parameter models, and they'll train them, and so on. And they show reasonable performance. And the cool thing is like once you train this thing, you can pick this parameter, like at what people call it test time. You could be like, oh, I'm gonna repeat this thing like 100 times if I have a really hard problem, and then you can run it and so on. Okay, I guess that's the end. This was far from my favorite lecture in terms of presenting, but hopefully you guys got the gist of things.
When you do this loop thing, do you train on the loop, or do you just first train the transformer and just use it as
You
is?
train it kind of like RNNs are trained. So you train it with like backprop through time sort of thing.
Okay, so
And then you like randomly choose the length so that it can perform well on different lengths of test time. So yeah, the question is like, right, at the end of the day, the theory stuff says that like there's gonna exist some set of parameters. And then you're gonna, like, after Dale's class, we're gonna get into what is called like learnability stuff, which is like, how do you actually learn the weights from data, right? Those different things. And the question is like, how are you gonna learn the weights from data to do this kind of behavior unless you train with this kind of behavior? And then there's actually problems there, because then you have the issues that you have to do this like backprop through time, and you can't parallelize the training like you can with chain of thought stuff, and then there's trade-offs and so on. So right now, yeah, like in terms of representing things, maybe this is better, but in terms of training, it's a whole other world. Yeah.
What do we know about tree of thought stuff? I don't know, these, I mean, it's like a path, but if they...
Yeah, I forget how the tree of thought stuff works. They like branch out or something, I don't know.
I think
But
tree of thought is unrelated pretty much to all of this. It is more like scaffolding put around transformers to use them for reasoning tasks. It's like you put a loop around the transformer that like it's not just autoregressive loop, but like some more complex post-processing, and then like there is some loop doing its thing, and like a tree is being built, and like there's some things happening, and yeah, that's.
It's not like a
scaffolding.
structure of the transformers, you mean? It's not like a structure of the transformers to put
Not
them.
at all.
I see.
But in a way, like when you are looping the transformer, you're kind of doing that. When you're auto-regressively doing things, and you're doing some scaffolding, it's just like the complexity of the scaffolding that you do is vastly different. Like in tree of thought and like these other things, it's vastly more complicated.
So maybe
It's
I
still
can...
not very complicated, like you can write it in a day.
I see.
Code for it, but yeah.
So maybe I can revise my question by, what if instead of a path, I mean, chain of thought is just appending the last, what if, for example, making more complex graphs?
yeah, I don't know of any theory stuff that.
That's not tree of thought, but it's like a
Yeah.
tree.
But the point is, you can think of all sorts of ways to augment this thing. Then you might, I mean, people like the representational arguments that people make usually is like, you know, people in practice have actually trained these things, so it's reasonable to talk about them.
Yeah.
And then like, given that they have been trained and so on, like which one is kind of like the more effective architecture or whatever parameter to scale for the problems you want to solve and stuff. Yeah, so that's kind of the line of work that people do here. And then there's all sort, there's like unbelievable amounts of paper of like, what happens if you have just like a one layer transformer about like different things. And then also this complexity theory stuff, like that's one way to pick functions and function classes. Other people, and actually someone in this class is gonna present it. There's a work, you can just like kind of arbitrarily be like, oh, I care about some function. Let's say function composition. That's a function. And I can be like, can transformers represent that? And the paper that people are gonna present is they're gonna say, well, maybe I won't ruin it, but they'll say things about it, which is exactly of this type. And they're gonna be like, oh, the transformer is going to mean at least this big or something to be able to do it, and something like this, so yeah.
You started with talking about two-state Turing machines. Do all the results only hold for two-state Turing machines, or do they generalize more?
No, like this is, yeah, it's any finite state.
So everything here is
Yeah.
for any finite state Turing machine?
This
Okay.
is just an example, so for people that don't know what a Turing machine is. It's like, this is maybe a bad example because you don't use the tapes at all, but it's just a finite state machine that also has access to some memory, and for all the Turing machine, like deterministic time and whatever, it's any Turing machine that has a finite number of states, so it doesn't depend on input length. So it could be gigantic, like billions and billions of states, but it's independent of n. So there's gonna be eventually an input that's like way, way bigger than it. That's the whole argument. Yeah. Here's like, there's all sorts of other cute results for things. Yeah.
In the transformer definition, like the transformer function class definition, you have for every input size, you have a different parameter. Right?
Yeah.
And so in the chain of thought, do you still have like different parameters for different?
The chain, so there's two different, like there's the case, okay, there was like two, the non-uniform thing is like quite literally people, that equivalence is quite literally allowing the transformers to have a totally different parameter for every single input size. But then somehow, and I haven't been able to write it properly and so on, these ones here with chain of thought actually results, they don't require this uniformity at all. And it's something of the type that like, for any input size, there's gonna exist like some set of parameters.
It's because the bits doesn't change, only
Yeah.
the precision changes. And so you can have real numbers there. Just
Maybe.
you use fixed precision calculation. So that's,
Yeah, the weights
that's
don't
how
change.
they are.
But the weights, no, they change in precision.
No, like you can have infinite precision weights, but when processing inputs of length n, you only use log n bits of it.
Yeah, maybe.
I think that's how it is.
Yeah. I don't know enough of the details, to be completely honest. There's a...
That would be plausible at least.
Yeah. But the chain, so the chain of thought stuff doesn't need it in this way, the non-uniformity stuff. And maybe the reason the non-uniformity stuff is like such a beautiful comparison to TC0 in these circuits is because in circuits you can see you need a different size circuit, or you need a different circuit for every input size. So that's why that relationship is like very nice. And so that's actually how the circuit classes are defined, is you'll have like a family of circuits such that from that family you pick the corresponding circuit for each input length. And here you would have a family of transformers such that you pick them. Yeah. Okay, that was way over time.